Seems so long ago now. We finished with this really terrible looking group of reduction formulas. Let me just remind you, you do not need to memorize them. Every semester, though, I seem to have someone that just feels compelled to memorize these. Like, who's it going to be this semester? It just seems crazy to try to remember those things. So the only ones you need to remember that are reduction formulas are, Jack did arrive. We were talking about you.
All of us.
The sine squared and the cosine squared. Those are the two you have to remember. Sine squared and cosine squared. But these random ones you don't. But if you were given these identities, you should be able to sort of move through it and make it work. So in this case, we had n was 5. So we're plugging in n equals 5 for all the positions that we see in n. We ended up with a secant cubed over here. Then we just do it again, rinse, repeat. And now we're down to this. And let me just write down this very final step. And we're going to talk about the integral of secant. The integral of secant is an integral that you will see quite a bit this semester, the integral of secant. And you do not know it yet, most likely, unless you've read ahead. But the chances of that happening, unfortunately, are less than they should be. You should always read ahead, because 2 hours and 15 minutes of math is a heck of a lot of math. If you get sort of mind blown in the first 20 minutes, you've got 2 hours left. So it's usually a good idea to look ahead and read ahead to try to be oriented. So I've distributed this 3/4, and the integral of secant is going to be the natural log of secant plus tangent. Not obvious. Not obvious. So that's what we're going to talk about now. Talk about why that is what it is. So we've done our reduction identity. We've repeated this formula a couple times. And then we get down to secant to the 1. And that's an antiderivative that you should become familiar with, because you'll see it a lot. So let's go to the next slide. And we're going to notice something. The 4 trig functions, other than sine and cosine, so the other 4 trig functions, other than sine and cosine, all are going to integrate to logs. So we know that the integral of cosine is sine. We know the integral of sine is minus cosine. So those two we've got dialed. But the other 4 you haven't really looked at in depth. All 4 will integrate to log functions. And anything that integrates to a log function can be put in log form before you do the integration. So the simple 2 are tan and cotan. Let's rewrite these with their quotient form. So there's the rewriting of tangent as a quotient. It's almost in log form. What is the one tweak we need to make? The minus sign. So for it to be in log form, the denominator's derivative has to be exactly the numerator. And we know that the derivative of cosine is minus sine. So we can do this. If we need a minus sign, we put a minus sign. But if we do that, we have to balance that by putting 1 on the outside. Because we can only multiply by 1. We can't multiply by -1. That changes the value. But we can always multiply by 1 and preserve the value. So if we multiply the inside by -1 there, then we multiply the outside by -1. Now it's in log form. So this will be minus natural log absolute cosine plus c. Everyone okay with that? Any questions? All right, how about cotangent? Go ahead and write cotangents quotient form down and see if you can write that one's antiderivative. See if it can be put in log form easily or not so easily, whatever. See what happens. What do we notice about cotangent when we write it in its quotient form? What do you notice? You write it as a quotient. It's in log form right away. Yeah, right? Because cotangent is cosine divided by sine. That's in log form right away. The derivative of the denominator is the numerator. So that's in log form. So we're done. We know that this will be the natural log of the absolute value of the denominator. So we have our antiderivative instantly. So those two are pretty obvious. A little bit of tweak with the first one, but overall pretty obvious that we can get it into this log form. And then it's always natural log, absolute value of the denominator. Secant and cosecant. If you look at any integration table, you'll see that they integrate to logs. And if they integrate to logs, that means you should be able to rewrite them in log form. And this is not obvious. It's not obvious how to rewrite that in log form. Here is the trick. I would definitely call this a trick. So we are, in fact, going to multiply by 1. We always do whenever we're trying to change the look of something, but not the value. We multiply by 1. And here is what we're going to multiply by. Someone remind me what the derivative of secant is. Secant x tangent x. So that is my hint. So we are going to multiply by something very close to secant x times tangent x. We are just going to turn the multiplication into an addition, and I claim that now it's in log form. That will put it in log form. Let's check. So definitely something that takes a little bit of remembering, first off, that that's what you have to multiply it by. But we will see this one so much that it should become second nature. So let's do a little manipulation here and just see if it's in log form. So we have secant over 1, so I'll multiply the numerators across. We're going to get secant squared of x plus secant x tangent x, all divided by secant plus tangent. And that's in log form. Let's observe. All right, the derivative of a sum is a sum of derivatives, so we just have to differentiate each part of the denominator. What's the derivative of secant? Sectan, right there. And the derivative of tangent? Secant squared, right there. So now it is in log form. The derivative of the denominator is the numerator. And we have the commutative law of addition. If we wanted to rewrite it, we could rewrite the denominator as tangent plus secant so that the derivative is right above it. It doesn't matter, though. We know the commutative law of addition. But this is in log form. So this tells us that the answer, the antiderivative, is natural log of the absolute value of the denominator. So that is our antiderivative for secant. In a similar way, this one we will see a lot less frequently. Secant you just see a lot. The integral of secant just seems to crop up a lot. With this one, we're going to do something very similar. We are going to multiply by 1. And we're going to use the same kind of hint. What is the derivative of cosecant? Negative cosecant cotangent. And so we're going to do the same kind of thing. We're going to break it apart, and instead of multiplication, we'll put an addition. And here's where you could do it in one of two ways. You could just multiply. What's it called? The upside down is coming after us. So you could multiply it by cosecant plus cotangent, or you could multiply it by minus cosecant minus cotangent. It's not going to really matter. So you could, so I said, you told me that the derivative was minus cosecant cotangent, so you could make that a minus cosecant and a minus cotangent. Or you could make it positives, and then we'll have to fiddle with the minus in a minute. It's not really going to matter. So the important thing right here is that we multiplied by 1. Right? Multiplying by 1 is always legitimate. So let's see if it's in log form or if it's log form-ish. Let's see what we have to do. So we get cosecant squared plus cosecant cotangent. All divided by, and I'm going to just reverse the denominator so that I have things lined up more like a columns, just because this one's a little bit trickier. So what is the derivative of cotangent? Minus cosecant squared, so we definitely need a minus there. And the derivative of cosecant? Minus cosecant cotangent, so we need a minus there. So what we just did was multiply the numerator by minus 1. If we multiplied the numerator by minus 1, the way that we counteract that, the way we balance that, is to multiply the front by a minus 1. This minus 1 in front, if it were to distribute in, we'd get back to where we were. So that's legitimate. We just multiplied by 1 again. Minus 1 times minus 1. Now it is in log form. Derivative of cotan is minus cosecant squared. Derivative of cosecant is minus cosecant cotangent. So that's log form. And this will be minus the natural log, absolute value, cotan plus cosecant. So those are the two more complicated ones in terms of showing that they are in log form. The secant one we're going to see a lot. So that's the one that's much more important to sort of get in your quiver. Mm-hmm.
So did the minus and the natural log come from the minus in the middle of the integral sign?
This minus here?
Yeah.
That minus is that one right there. These minuses have to be in here because the derivative of this is negative and the derivative of that is negative. So the minus out in front is the one that stays out in front. Any other questions? Okay, so all 4 trig functions other than sine and cosine integrate to logs. Lots of logs. All right. This is a classic example that you'll see in every single calculus book. We can integrate, when we see this secant cubed, you immediately, perhaps, since we had the slide up earlier today, we immediately think of that reduction identity, that secant to the n, and we could use that reduction formula. But secant cubed is actually a special case where we can use integration by parts with a twist. We can use ultraviolet voodoo with a twist to integrate that. And let's check it out. So I'm telling you, I'm giving you a hint that we are going to use a twist. And anytime we use integration by parts with a twist, that's the scenario where we get like integrals on either side of the equal sign, and then we sort of twist them together. You know, and it feels a little funny because we're twisting an improper integral with another improper integral. We don't often think of integrals as being like and then combining them. So, but we can do that. We need a little more space here. So this is going to be our integration by parts formula here. We're going to prepare for the formula with this little table. So this right here, secant cubed, we need to turn it into a UdV. So remember that the integral of UdV, integration by parts, will turn into UV minus the integral of v du. So there's our ultraviolet voodoo. And we want to put with the dv the biggest chunk that's easily integrable. Secant squared is the biggest chunk of that that's easily integrable, because we know the integral of that's tangent. So that's why we're going to put secant squared with dv, because we can integrate that super easily. If you put secant there, you would integrate and get natural log of secant plus tangent, which is kind of messy. And then you'd also have to differentiate secant squared, which would be a total mess also. So this is going to be the easiest way to subdivide the integrand and have something that's pretty easy to integrate and something that's pretty easy to differentiate. So now let's see what happens. So whenever we do this twist, we always call our integral something. And we pick our favorite letter, whatever. I'm going to use that letter, omega. Greek letter, omega. So omega, that's the left side of the equal sign. That's this improper integral right there. Integral. If you want to rewrite integral of secant cubed again and again and again, you can. It's just a little easier to pick a letter to represent it. So uv, that's the main diagonal right there. So secant tangent. There's uv. Minus the integral of v du. So minus the integral of voodoo. Bottom row, voodoo. That's going to be secant times tangent squared. Secant times tangent squared. Okay, so now we have an integral with powers of secant and tangent. Now let me just go back for a second. So here was our original sec-tan, product of powers. And remember that we had two rules. If secant was to an even power, we pulled off secant squared, thinking that we could let u be tangent, because if we let u be tangent, the derivative of tangent is secant squared. If the power was odd on tangent, we pulled off a sec-tangent with the plan of letting u be secant, because the derivative of secant is secant tangent. So those are our two rules. If secant is even, if tangent is odd. Now if neither is true, so if secant is odd and tangent is even, we're going to convert the tangents with the Pythagorean theorem. So that's the case we are in with our case here. Secant is not to an even power, so we can't pull off secant squared. Tangent is not to an odd power, so we can't pull off sec-tan. So all we can do is go to the Pythagorean theorem. We can't convert secant because it's not to an even power, right? Pythagorean theorem has a bunch of squares. So that thing right there can be converted with the Pythagorean theorem. So again, I would highly recommend knowing this picture. It makes memorizing the identity so much easier for most people. That's on a unit circle. That picture shows us that 1 plus tan squared is secant squared. That is the best way that I've ever seen to memorize this identity so you don't get it tangled up. All right, so let's replace tan squared. When we look at our identity, tan squared is secant squared minus 1. And we have that. Distribute. So we'll have our integrand being secant cubed, ding, 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 minus, that will be secant, dx. So that's secant cubed in there. That matches the left side of the integral. Our omega represents the integral of secant cubed. So we're almost ready to do the twist. Almost ready. So we'll have this. Now we're going to distribute the integral symbol. So we're going to have minus the integral of secant cubed. That's just omega. Right? The integral of secant cubed, that's what we said omega is going to represent, the integral of secant cubed. So the minus sign with this integral, we have minus omega, and then we have plus the integral of secant. And on the left side, we have an omega. So now we're going to do the twisting business. The omegas are going to combine into they're like terms, so they're going to combine to 2 omega on the left. And on the right, we have the integral of secant. We've talked a little bit about already. Integral of secant is natural log of secant plus tangent. Plus a constant of integration. What's our last step? Divide by 2. Isolate that omega. We want to know what omega is. Omega is the indefinite integral of secant cubed. So we solve for omega, and that's our last step. So that will be how we can, once again, use integration by parts to integrate something that is pretty complicated. And when you go back to that prior slide with all those reduction formulas, that's actually how you prove those identities, is with repeated integration by parts. But again, you do not need to memorize those unless you're crazy. So notice that dividing by 2, this constant divided by 2 is yet another constant. We don't need to write it as c over 2. We can just think of it as a new constant. That is the constant for this equation, different from the constant up here for this equation. So we think of the constant like a recycle bin. Everything that's constant just sort of goes into it and stays a C. Any step there that you are wanting to ask about? No. Yeah, you want to know your Pythagoreans. Yeah, good question. You need to know your Pythagoreans. Those are essential. Essential. And having a visual, so the main ones we're going to see are sine squared plus cosine squared is 1, and then this one. We're not going to do a lot with cotan and cosecant. So this one is the one that you really want to have down because we go back and forth between secants and tangents just a lot. And having that, not having it down just makes a bunch of busy work all the time. So having this down is super helpful. That picture should make it crystal clear, I hope. And here's the other one for the sine and cosine, right? This is the one you see all the time. There's one, cosine is that direction, sine is this direction. All right, same idea. And some of you might be interested in why this triangle is what it is. Does that apply to anyone in this class? Is there some curiosity? So everyone knows about similar triangles. Similar triangles have corresponding ratios that are equal. So if you have similar triangles, similar right triangles, the rise over the run has to match. So these two triangles are similar. This triangle up here, all we did was extend the terminal ray out. We just went up and then extended it and built that triangle. So the sine-cosine triangle is similar to the triangle above. They're similar. So we're starting here. We extend out and build that triangle. That tells us that the rise over the run of this little triangle has to match the rise over the run of the bigger triangle. Okay, well, when we look at the little red triangle here, the rise over the run is sine over cosine. Sine over cosine is tangent, right? Sine over cosine is tangent. When we look at this triangle over here, let's imagine that we don't know what these are yet. But we do know that that's 1, because this is a unit circle. So if we extend this terminal ray out and drop it right down to this point, I'm an eraser. Right down to that point right here, this dimension right there is 1, because it's a unit circle. So if the rise over the run here has to match the rise over the run here, what does the vertical side have to be? If you divide by 1, the rise over the run here is tangent. So the rise over the run here has to be tangent. But if the run is 1, the rise has to be tangent. There's no other choice. Right? If we want the rise over the run to be tangent and the run is 1, the tangent has to be the rise. It has to be that vertical side. And then you can do the Pythagorean theorem to get that, okay, well, if that's 1 and that's tangent, then that has to be secant. So, good little memory trick for that secant and tangent identity. The other thing that this does, it just shows you the relationships between secant and tangent very visually. If someone says, maybe before you look at this triangle, if someone said, is the secant of 1 million radians bigger or smaller than the tangent of 1 million radians? Most of us, without knowing that picture, might not have a good idea. But when you look at this picture, it's obvious. Secant's always bigger than tangent. Secant's the hypotenuse, right? That's always bigger than that. So secant is always greater in length than tangent. So it gives us a good visual for the relationship between the two. It also shows us very clearly that as theta rotates towards pi over 2, tangent of pi over 2 is going to be undefined because we can't draw that triangle anymore. And when we're at pi over 2, we can't extend the terminal ray high enough to get a vertical line that touches 1, 0. So it's a visual reminder that tangent is undefined at pi over 2. It's also a visual reminder that secant's undefined at pi over 2, because there's no triangle at all, so there's no hypotenuse and no vertical. And mentally, we could also just do it algebraically. Tangent is sine over cosine, so there's a cosine in the denominator. Secant is 1 over cosine, so there's a cosine in the denominator. And at pi over 2, what's cosine? 0. So we're dividing by 0 in both cases. So you can think of it analytically as division by cosine, which is division by 0 if you're at pi over 2, or you can think of it visually that you just can't make those triangles. Okay, so that brings us to trigonometric substitution. This is the integration technique that many of you will wrestle with like, wrestle like crazy children. It will drive you a little nuts. But we're going to try to break it down into some simple ideas. So trigonometric substitution, first off, notice that all these Pythagorean identities, there's a 1 in them. You know, sine squared plus cosine squared is 1. Tan squared plus 1 equals secant squared. That's kind of the hint that we're going to be using trigonometric substitution. So trigonometric substitution and the Pythagorean identities are two sides of the same coin. And in general, in the big picture, you should be thinking trig sub when you see a sum of squares or a difference of squares. So I'm going to call this a sum of squares. And you could have the one in front or the one trailing. It doesn't matter. I would refer to that as a sum of squares with a leading 1. This is a difference of squares with a leading 1. This is a difference of squares with a trailing 1. So these two are a little bit more important to distinguish where the 1 is, because up here, the 1 is positive. Down here, the 1 is negative. So we'll say that's a difference of squares with a leading 1 versus a difference of squares with a trailing 1. And our goal, like we've seen a lot, when the denominator is 2 terms, that's a problem. You can't split a fraction when the denominator is 2 terms. If the numerator is 2 terms and the denominator is 1 term, then you can split the fraction. Right? You can take that 1 term and share it with the numerator. You can distribute it. And this is our goal. If you look at those Pythagorean identities here, what the main idea, I guess I didn't write, where did I write them? I wrote them somewhere, I thought. Maybe I didn't write the Pythagorean identities. The main idea is that you're taking 2 terms, adding or subtracting, and changing that into 1 term. Sine squared plus cosine squared equals 1. That's 1 term. Tangent squared plus 1. Those are 2 terms, but that's equal to secant squared, which is 1 term. So that's kind of our underlying strategy to kind of take two terms and turn them into one. And that's what the Pythagorean identities do. They take two terms and turn them into one. So that's going to be our goal. So, for example, if we had something like 1 plus tangent squared right here, if the u was tangent, 1 plus tan squared is secant squared, right? That collapses these two terms into one term. If, for example, we let the u be sine, that's a minus. If we let the u be sine, what is 1 minus sine squared? Cosine squared. So we've taken two terms and we've compressed them into one. Down here, if we just say, hey, what about if we let that u be secant? If we let the u be secant, what is secant squared minus 1? Here's our triangle again, just as a reminder. Tan squared. Secant squared minus 1. Hypotenuse squared minus leg squared is going to be the other leg squared. And this is the heart of trigonometric substitution. There are three possibilities that we are going to use for trig sub: sine, secant, or tangent, depending on whether we have a sum of squares or a difference of squares, depending on whether we have a leading one or a trailing one. Those are the only three functions we use for trig sub: sine, secant, or tangent. The tangent one's usually the easiest to remember because tangent, the t looks like a plus, and it's the one that has a plus in the middle. So tangent's always going to go with the plus. And then these, we have to use a little bit of thinking. Is it 1 minus sine squared that is an identity? Or is it 1 minus secant squared that's an identity? And 1 minus secant squared would be negative tangent squared, which is not what we want. That's not going to be helpful. You'll see why once we get to it. So 1 minus sine squared, that's definitely an identity right there. Secant squared minus 1 is definitely an identity right there. So those are the three that we're going to use. Only three: sine, secant, or tangent. So here we go. So this just kind of restates what we just did. The triangles I have right there as a reminder. So it's going to be sine, secant, or tangent. If it's plus, we're going to let the u be tangent. Over here, we're going to let the u be sine. Here, we're going to let the u be secant. So those three. All right, so ready? Let's do our first one. So look at that slide again carefully to try to reinforce. So when we look at this, in this integral, we look in the denominator, and we have the square root of a difference of squares. We cannot break that square root apart. Square root cannot be broken apart when you have a sum or a difference. If it has multiplication, yeah, you can break it apart, but not here. So we are going to do two things here. The first thing is, it's so much easier in the long run. You just have to trust me on this. If you look at the integration tables, they're going to rewrite this as 2 squared minus x squared, and they're going to say a is 2, and they're going to have a formula with a 1 over a or an x over a and a bunch of different things. If you do it that way, you have to memorize 3 extra identities other than the basic 3. The basic 3 that you need to know are that the integral of 1 plus x squared in the denominator, that's our tan, that's our basic one. And maybe I'll put a u in here just to make it easier to later. So if we have that, that's our basic inverse tan identity, no problem. But if this is not a 1, you have to manipulate it. And you have to either put u over a, 1 over a, and there's 3 extra things that you have to do. My strategy is going to be to always make it a 1, because then we just have to memorize 1 integration formula instead of 2 for each of the trig functions. And then we'll use reverse chain rule. So these are the basic 2 that we are going to use the most. These are the ones that you will see by far more than the inverse secant one. So those two you really, really want to have dialed. So we know when we just sort of glance over, it's like, oh yeah, this has definitely got some sort of, looks like some sort of inverse sine thing in it. But of course, that x squared throws everything off. Right? It's not just an antiderivative that's some modification of inverse sine. That x squared messes that all up. Right? If it was just a 1 up there, then it would definitely just be an inverse sine. OK, so here's what we're going to do. We've got a difference of squares. That doesn't change. But what we want is a difference of squares with a leading 1. So we have to do some algebra. So let's factor out the 4. So that 4 is coming through a square root in the denominator. So when a 4 comes through a square root, it turns into a 2. So we factored out that 4. We have that. And here is the step that we have to be comfortable with basic algebra. We are factoring a 4 out of something that doesn't have a 4 in it. So what that will do, you can think of it in a couple of ways. So if you want, you can say, OK, here's 4. I can multiply this x squared by 4 over 4. And then when you factor out the 4, you're left with 1 minus, so this is the 4 that's coming out to the front, right there. So we're left with 1 minus x squared over 4. Everyone follow that? So if you're pulling a 4 out of something that doesn't have a 4, it puts 1 in the denominator. How do you check that what you did was right? You go backwards. You distribute. If you distribute that 4, you better get back to where you started from. And if you distribute that 4 to the second term, it cancels with the denominator. And you get back to just the x squared. And then the final step of the algebra is that we're going to want to write this as a difference of squares. So we have to do this little factoring type thing. We want to write it as a difference of squares. So that's going to be our strategy. Algebra, a little bit of algebra. So when we factor out the 4, this is what we are going to have over here. Now we have a difference of squares with a leading 1. And that's going to be our key. All right, so let's ask if you have a question on that before we go on, because that's essential. To be able to do that algebra is essential.
I'm just a little confused. I just wanted to ask the square root.
What's the square root of 4?
2.
So this
Right.
right here is inside the square root. So if we put the square root right there, the square root of a product you can separate. So the square root of the 4 comes out in front, and then we're left with the square root of the other piece.
Okay.
Does that make sense?
Yeah, that makes sense.
Other questions on that before we do our substitution?
Why did you pull out the 1/2, or you put the 1/2 there?
So we want to write, so we're trying to line up and have a difference of squares with a leading 1. So the second term needs to be something that's squared. And when we have it in this form, that's not a quantity squared. That's x squared over 4, so the x is squared, but we want to write it as a quantity that's squared. So we want to be able to identify what the u is. And so this step right here, this is written as a difference of squares. This is almost written as a difference of squares, but to be a difference of squares, it has to be something squared minus something squared. So that's our goal, is to have that second part be a quantity that's squared. Okay, so now we're ready for the use of, for the trig substitution. So we look up here, let's go with green, and we have a difference of squares. So we want to let the x over 2 be sine, secant, or tangent. We know it's not tangent. Tangent's always the one with the plus. So it's sine or secant. And we have to ask ourselves, is 1 minus sine squared a known identity? Or is 1 minus secant squared a known identity?
Sine squared.
1 minus sine squared. 1 minus sine squared is cosine squared. So we are going to let x divided by 2 be sine of theta. Because then inside the root, we are going to turn it into one term. And you can take the square root of one term. You can't take the square root of the sum or difference. But you can take the square root of one term. So that's going to be our goal. Turn what's in that root into one term. So let's see. Now we take the derivative of both sides. We're going to get 1/2 dx is equal to cosine of theta d theta. So there's our substitution. So we'll come over here. So this will be 1/2. We're changing over to theta, so we're going to have to convert these limits. Let's see, we need more space. Let's move this to over here. So the limits of integration, let's talk about that for a moment. You know how to convert limits of integration from your substitution step. With trig sub, usually it's better to not deal with them and just convert back to the original variable in the end. Usually with trig sub, that's the better move. So what I do, somehow you have to indicate that these are no longer, like we can't use the 0 and the root 2 anymore. So I'll usually just put little stars here to say, okay, we're going to go back, we're going to convert back to the 0 and the root 2 in the end. But when we do our conversion over to theta, we're just not going to bother finding those limits. We're just going to put some placeholders there until we convert back to the original variable x. Okay, so the numerator, x squared. Come down here, and we see that we can isolate x, and x is going to be 2 times sine theta. So x squared, 4 sine squared of theta. Now, dx. Those of you that are really sloppy and not writing your differentials, it is going to come back and spank you here. Because if you don't have that differential in there, you're going to miss out on a whole big chunk of stuff that has to be put in the integral. If you isolate dx here, you see that that's what dx is equal to. So now that has to get replaced. So now we have 2 cosine theta times d theta. So there is the whole numerator, including the differential. Now the denominator. Square root 1 minus x over 2 is sine, so 1 minus sine squared. And that is the pivotal move right there, because this is going to turn into cosine squared, and the square root of cosine squared is going to be cosine. And then that will cancel with that cosine. Now we've talked a little bit about the square root of cosine squared. The square root of cosine squared is only cosine if you're on the correct interval. You have to be, we talked a little bit about the square root of x squared it's a piecewise function. It's equal to x only if x is greater than or equal to 0. Otherwise, it's equal to negative x. So we'll have to make sure that that's true. The way that we would make sure that's true is right here. If x is 0, what is the angle? We have 0 over here. Sine of what is 0? Sine of 0 is 0. Sine of 0 radians. And then right here, if you did it as square root of 2 over 2, sine of what angle is root 2 over 2? Pi over 4. So the angle is between 0 and pi over 4, which tells us cosine is positive. And on these ones, the trig sub is complicated enough. They're not going to throw that in, as an extra tweak that's going to make you, pull out your hair. I think there is one example in this section, or in this chapter, where they do that. But in general, if they put the limits up there, it's going to work. Don't bang your head too hard on that part. The more important part at this stage is picking the right substitution, differentiating, and substituting properly. That's much more important at this stage. So constants to the front. 8 divided by 2 is 4. And we'll write every single step of this one down so we don't miss a beat. In the denominator, 1 minus sine squared is cosine squared. And we don't know these limits yet. We're going to go back. All right. And then square root of cosine squared is going to be cosine. And that whole thing, square root of cosine squared is cosine, that's going to wipe out this cosine. Cosine divided by cosine is 1. Square root of cosine squared is cosine. Okay. And then we are left with sine squared. And to integrate sine squared, we power reduce with that half angle formula. That's right. Exactly. So the power reduction for sine squared, there's a half that I can pull to the front. Power reduction for sine is 1, and there's a cosine of 2 theta over here, and is it plus or minus? Minus for sine. So we get that. This will give us 2 multiplied by integral of 1 with respect to theta is theta. The integral of cosine is sine. The angle is not just theta, though. We have a 2 theta, so we have to do an RCR. So we have to do a reverse chain rule. We have a linear angle, so we have to do a division by 2. And then we have these limits that we are going to convert back to in a minute. So any question on that integration step?
Can you just like go from the beginning and like run through it really quick?
Which part?
Just like the whole thing.
The whole problem?
Yeah.
Start from the beginning?
Well, like just like.
Sure. We can do it.
Okay.
The beginning's not far away. It's right there. So the first thing we did was factor out 4 from here because we want the inside to be a difference of squares with a leading 1. So we factored out the 4. So there's our algebra step. We factored out the 4. And when the 4 comes out of x squared, there's no 4 there, so it puts a 4 in the denominator. And then we want to write that as a square. So we write it as x over 2 squared. And then the trig sub, so this is just setting it up for trig sub. We want to have a sum or difference of squares with a 1. Leading 1, trailing 1, whatever. Once we have it set up for trig sub, then we have to decide sine, secant, or tangent. And if it's a difference, it's either sine or secant. And if it's a difference with a leading 1, it's sine. If it's a difference with a trailing 1, it will be secant. Because 1 minus sine squared turns into cosine squared, whereas secant squared minus 1 turns into tangent squared. So if it's a difference with a trailing 1, we're going to use a secant. If it's a difference with a leading 1, we're going to use a sine. We take the derivative of both sides here. Derivative of x over 2 is a half. Derivative of sine is cosine. And then we substitute. So x squared, isolate the x here as 2 sine theta. Square that, you get 4 sine squared. The dx, we isolate the dx. That's going to be 2 cosine theta d theta. So here's dx right there. And then the x over 2 is sine. 1 minus sine squared is cosine squared. So it's like a big jigsaw puzzle. And it's going to get more jiggy in a second. In a second. And then the integration part, sine squared, to integrate sine squared, we have to use power reduction for sine squared. And sine squared reduces to 1 minus cosine 2 theta over 2. So that's our power reduction for sine. And then the 2 is in the denominator, so it factors out like a 1/2. Right there, combine those, integrate. And what do we have to do now? Our original variable is x. we're dealing with thetas, we have to go back. So we usually call it back substitution. And so we usually go to our let statement and say, okay, let's go from theta back to x. But we have a sine of 2 theta. Up here, we only have a sine of 1 theta. So there is another identity that we are going to need to use in order to get back to x. That is called the double angle identity for sine, which is equal to this. Sine 2 theta is 2 sine theta cosine theta. So that is going to be another very important identity. You are going to have to use this one a ton also. Not as much as the power reduction, but. So sine of 2 theta right here, 2 sine theta cosine theta. Replace it with that, and we have cancellation of the 2. And now we have sine of theta, cosine of theta. So now we have a single angle down there. We still have these weird limits that we haven't figured out yet. So now we have that. But we're darn close, because up there we know that sine of theta is x over 2. All right. So now the next jiggy piece is we use a visual way to replace the thetas with x. This is where you can be creative. So here is a triangle, a right triangle. Every single time when you do trigonometric substitution, you're going to have to draw this right triangle. So this right triangle is a visual back and forth between theta and x. And we're always going to put theta right here. So we're going to draw this triangle like it's sitting in quadrant 1. All right, that's what it looks like, sitting in quadrant 1. Right there. Sine of theta is x over 2. So we come down to this cool triangle. We say, hey, sine of theta is x over 2. Sine is opposite over hypotenuse. Sine of theta is opposite over hypotenuse. So every trig sub is going to have this key triangle that's going to allow us to go back and forth. It's a portal that takes us back and forth from theta to x or x to theta. How do we find this leg down here? What's that got to be? Third part of it, square root of 4 minus x squared, Pythagorean theorem. Hypotenuse squared minus the other side squared, all square rooted. So Pythagorean theorem. And 99% of the time, this missing side should match something in the original integral. If it looks completely different, you probably did something wrong. So with this cool triangle here, it's going to connect you back to the original problem. And what this triangle does is allow us to go all the way back to x very easily. Okay. So first off, let's deal with the theta first. The triangle is going to allow us to get these two guys really easily, sine and cosine. When we look up here, x over 2 is sine of theta. Let me just write that off on the side here. So x over 2 is sine of theta. What does that mean theta is equal to? 100%. Inverse sine of the other side. So that's how we get the theta. We isolate theta in the let statement. So this will be inverse sine of x halves minus sine of theta is x halves. Right there, sine of theta is x over 2. Or you look at the picture, sine of theta is x over 2. Cosine of theta, you look at the picture. Cosine of theta is adjacent over hypotenuse. And now we're back to our x limits. We got all the way back to x. In general, with trig sub, it's way smoother to go back to the original limits instead of trying to switch them to thetas. All right, so questions on this stuff in here, going from here to here, getting back to x from the u sub? or not the u sub, the trig sub? Is there a piece there, Jesus?
I had a question when it was about that. It was just that
Sure.
it all makes sense. I was just wondering why setting x over 2, that expression, setting that equal to sine of theta, why is that a legal move? Why can you do that?
So why can we do this?
Yeah.
So we can do any substitution we want if the derivative of the substitution matches something in the integral. So we could even, if we wanted, we could let u be x over 2. We could let u be 1 minus x over 2 and try to write this, difference of squares. You could write it as 1 minus x over 2 and 1 plus x over 2 if you wanted. It's not going to work, but you could let u equal whatever you want. So you let u be something strategic. You can, some u's are going to be better than others. So here we're going to let, instead of just doing a regular u sub, we're going to choose to let u be a trig function instead, which we can do as long as we then incorporate the derivatives. So this piece right here is super important. When we do a regular u sub, we find du dx, and we have to do a conversion with the differential also. Here, it's just more complicated because we're not choosing just a polynomial or something, a 1 minus x or 1 plus x squared. But as long as we take that derivative with us, we can do a change of variable.
Okay.
The question really becomes, is it going to be helpful? And so what we know with trig sub is that it's helpful when you have a difference or sum of squares. So we could try a whole bunch of other substitutions that aren't going to work. We take the derivative, we substitute in, we get something that's unintegrable. But with trig sub, if we have a sum or difference of squares, it will work. So that's why we choose trig sub here. But you can let u be anything. You can do any kind of sub that you want as long as you also change the derivative and bring everything with it. The question often becomes right here. Can you integrate what you're left with? And so with trig sub, it will work really well with sums and differences of squares. So let's plug in. Let's plug in our limits of integration and see what we end up with. Let's notice first off that 0 is not going to give us anything. If we plug in 0 right here, this term goes away. And what is inverse sine of 0? Inverse sine of 0 is the angle that has a sine of 0. 0. The angle that has a sine of 0 is 0. So that's not going to give us anything with the 0. So let's focus on the upper limit. So we're going to have 2 arcsine root 2 over 2 minus root 2 over 2 times square root of 2 over 2, another square root of 2 over 2. And what is arcsine of root 2 over 2? So that's the angle on the right side of the unit circle that has a sine value of root 2 over 2. Inverse trig functions, first thing that should come into your mind is that it's an angle. Inverse sine and inverse tangent are always angles on the right. Inverse cosine is an angle that's on the top. So they're restricted angles. So this says, what is the angle on the right side of the circle that has a sine value of root 2 over 2? Bingo, pi over 4. That's where we have a sine value of root 2 over 2. So that is going to be pi over 4 times 2, which is pi over 2. And then over here, this is going to be a 2 over 4, which is a half. But then we distribute that 2 and we get a 1. So that will be our final result. So that is trigonometric substitution. We need to do a bunch of those.
I'm still confused on the power reduction.
Mhm.
I don't really know how that works.
So the power reduction for us, the ones that we are going to see repeatedly, are when we have an even power of sine or an even power of cosine. And so what we're doing is taking the power of sine here is 2, the power of cosine over here is 1. So that's what we mean by power reducing it. We're taking the power of 2 on sine and we're reducing it to a power of 1 on cosine. And so this identity is from the double angle identities for cosine. So I showed you how we got this originally, but at this stage what we want It's just anytime we see a sine squared or a cosine squared and we have to integrate it, we need to use that identity. So sine has a minus there, and cosine squared has a plus there. And so that's the only way we can handle that thing. You could say, oh, well, can't we write it as 1 minus cosine squared? Yes, you can, but then you have to integrate cosine squared. And the only way you can do that is with power reduction. So sine, even power, so sine squared and cosine squared, you have to power reduce. That's going to be the trick. All right, let's take a 10-minute break. 10-minute break now. Set, go. And let's see. They're graded. And let's see. Can I just I need to bring up somebody's. Jack, do you mind if I bring yours up?
Sure.
Is that okay? So you can say no.
No, yeah.
Mine's
I don't
blank,
mind.
you wanna look at that one?
No, that's okay. So if you
I didn't know you were talking about the old one.
okay, so first off, yeah, notice that the new worksheet's been released. So chapter 8's been released, everybody, so you'll see that. So here's the original one, and you'll have a score up on the top of it. And then I created this corrections worksheet because I want those of you that didn't get full credit to come in and fix the ones you didn't get full credit on so that then I can give you full credit. So I just copied the worksheet again. I didn't want to just reopen this one because then it gets messy. What did you do before? What's new? But now then whatever is new is obvious. So you only have to insert answers for the ones you didn't get right. The ones you got right, you don't have to re-enter for those. So just the ones you didn't get right. And if you didn't do anything, you can do it again, or you can do it for the first time, I guess. You can do it for the first time, and I'll give you up to 4 points for it. And then the due date is Monday, March 6th by midnight. So it's 2 weeks out, I think. About 2 weeks out. Two weeks in a couple days. Something. All right. Any questions on that? And then once once that due date has come, then I'll enter them in the grade book and I'll release the key, which if you need it. Hopefully by then you won't need it, but if you do, that's fine. And then the chapter 8 one is released now, so there's some integration. You should actually be able to do the first couple pieces of this now. So there's an integration by parts thing. There's a powers of sine and cosine, and then there's a trig sub. And that, oh yeah, and an improper integral. This you can't get to yet. But so that one is ready for you to start fiddling with. And if you have questions as you start doing it, of course, ask. Let's get back to chapter 8. All right, let's try another trig sub. Oh wait, we had one more on that previous slide, I think, at the bottom. Yeah. Okay. So any questions on the worksheet, or does that make sense enough? All right. Okay, so let's do another one here. So again, basic strategy is going to be trig sub if we have a sum or difference of squares that you can't do with regular u sub. So we look in here and you think, okay, well, if we let u be what's inside the square root, that's not going to work because the derivative is not on the outside. So whatever we choose for our sub, whether it's a u sub or a trig sub, the derivative has to match something that's in the integrand or you can't go anywhere. And so here, regular u sub's not going to work. So we're going to go with trig sub because we see a difference of squares. Now, the strategy that we are going to use in this class is that we want it to be a difference of squares with either a leading or a trailing 1. That's going to make our life a lot easier. Question?
On the test, are you gonna tell us how to solve each problem, or are you just gonna give it?
I'm not going to tell you how to solve each problem.
Well, like,
Unless you give me a lot of money.
are you gonna be solve this with use?
I will tell you what to use, though. So if it's trig sub, I'll say use trig sub. If it's integration by parts, I'll say integration by parts. But I won't say use trig sub and let u equal sine of theta over 2. I won't go that far.
You say we're gonna have to know it's useful
Pythagoreans?
No, the double identity, the sine of 2 theta double.
Yes.
Is it also, do we also use the cosine of 2 theta identity a lot?
No, not directly. Not directly. We use the power reduction ones like this. This is a rewrite of the double angle for cosine. So we are using the double angle for cosine within the power reduction identity. But we won't use it like the cosine 2 theta equals cosine squared minus sine squared. We won't use that too much.
And you said not use sub because what was
Yeah, so there's not a t on the outside. If there was a t out here, then regular u sub would work because the derivative of the inside here is minus 2t. But if there's not a t on the outside, then there's no way for the substitution to work. There'd have to be a t on the outside. So that's what sort of tells us, let's try trig sub instead. Okay, so when we factor out that 36, what is going to go to the right of that minus sign? T over, there's two things. Let's do it in two steps. So it could be t squared over 36. But then if we write it as a difference of squares, it becomes t over 6, thank you, quantity squared. Yeah, so there's the algebra. Now it's set up perfectly for trigonometric substitution. We have a difference of squares with a leading one. Now it's set. Now we ask ourselves, sine, secant, or tangent? Sine, definitely not tangent because it's not a plus. So it's sine or secant. And sine is the one that has the identity 1 minus sine squared is cosine squared. So this one's going to be a sine. So we are going to let t over 6 be sine of theta. Take the derivative of both sides. So we're going to have a cosine of theta times d theta. And if you need to isolate the dt, a lot of you don't even do this step. That's totally fine. If you can just see that dt is 6 cosine theta. All right, so now we have to replace anything that has a t needs to be replaced with thetas.
so like why are we using theta?
Because, what, do you want to use a different letter?
Well, no, just like
So we're going to use trig sub because u sub is not going to work. So whenever we see a sum or difference of squares, usually trig sub is going to be the way to go. So right here we see a difference of squares. And so that 90% of the time that means go trig sub. And if you're going trig sub, then you have to pick a sine of theta, cosine, sine of theta, tangent of theta, or a secant of theta. So that's how we decide to go with trig sub, because we see a difference of squares. And then we do our substitution, and we're going to have 6 integral square root 1 minus sine squared, because that's what we let sine be. And then we have to do the dt, so that's going to be 6 cosine of theta d theta. So now we've turned all the t's into thetas, and we're going to hope for the best. So 36 out in front. And so here is a great example of what I mean by the book doesn't always clarify. Let me write this and then I'll mention it. So the book does not always clarify that cosine of theta is going to be positive here. So if you end up with the square root of a square, we're just going to assume that you can take the square root. Unless they actually tell you that you can't, or if they give you an interval on which it should be negative, bless you, then we won't. But if they give us no information, we're just going to assume that the square root of x squared is x. So they give us no information. Okay, so we are going to say that the square root of cosine squared is cosine. So then we're going to have cosine times cosine, which is cosine squared. And now we're going to use power reduction. We have power reduction for cosine. Very good. So power reduction for cosine, we're going to pull out 1/2. And that's going to be 1 plus cosine of 2 theta. And then both those terms are integrable. So we're going to have 18 parens. Integral of 1 is theta. Integral of cosine is sine. But then we have to do reverse chain rule, divide by 2. And then constant of integration. And this is going to be similar to the last one. We don't know anything about sine 2 theta, so we need an identity. We're going to rewrite that as 2 sine theta cosine theta. So now we want to reduce the angle. Sine of 2 theta gets turned into 2 sine theta cosine theta. Cancel out the 2's. Now we need that cool triangle in order to get back. We need to get back to t. So t over 6 is sine of theta. So let's come over to the side. T over 6 is sine of theta. So first off, this tells us that theta is what? Sine inverse of t over 6. Exactly. So that is how we would isolate theta. Good. And now to build the triangle, we always build it like it's in quadrant 1. So it's sitting in quadrant 1. Sine of theta is t over 6. So that's rise over hypotenuse. So we're going to do that. And then what is this side down here? 36 minus t squared inside that square root. And that should match something up in the original integral. If it doesn't, if it's totally different, then something's wrong. It should match pretty well. So this will give us. And let's distribute the 18. There's no point of having the 18 just factored out of these two terms and not that. So 18 theta, so 18 arcsine t over 6. And then the 18 distributes here times sine of theta. Sine of theta is t over 6. Times cosine of theta. We look at our triangle. Cosine of theta is adjacent divided by hypotenuse. Then we just have a little bit of simplification with these constants. 6 goes into there once, goes into there 3 times, and then 3 goes into there once, and 3 goes into there twice. So we end up with a 1/2 coefficient when all is said and done.
When you're integrating.
So integrating 1 gives theta. Integral of 1 with respect to theta is theta. Derivative of theta is 1 if you're differentiating with respect to theta. Integral of this function, note that we have a linear angle. So if we have a linear angle, that means we have to do our reverse chain rule. So the integral of the function, the integral of cosine is sine. Angle doesn't change. Right? Angle never changes when you're integrating or differentiating. So integral of cosine is sine of the same angle. But then because that's a linear angle, we differentiate the angle and divide. with the reverse chain rule. Time to do one other than sine, I think. We've done 2 sines. All right, let's do another one. These things you just have to do a bunch of them to start to, once you get the process and the triangle, then it starts to feel less new. Oh, yeah, that's how you make something feel less new. You practice. Yeah. Imagine. All right, so when we look at this, we see a sum of squares. Anytime we see a sum of squares or a difference of squares, we should be thinking trig sub. Or on the test, if it says use trig sub, that's another way. If you're told. So what do you think? Sine, secant, or tangent?
Tangent.
Tangent. We've got the plus. Tangent. And look, there's no algebra. Right? We don't have to do any algebra here. So we're going to let x equal tangent of theta. That's going to be our substitution. Do we recognize that we couldn't integrate this directly? Do we see that we couldn't integrate this directly? If this was a 1 plus x and not a 1 plus x squared, we could integrate it directly. Then we could just do the 1 plus x to the negative 3/2, add 1 to the exponent, divide by the new exponent, and do a reverse chain rule if possible. But that's not, we can't do that here. Because the derivative, this is not linear. If this was linear, you could do it with the negative 3/2 thing. But it's not. The derivative of 1 plus x squared is 2x. And there's no x in here. If there was an x here, then u substitution would work just fine. But there's not an x there, so u sub does not work. So derivative of both sides here. So derivative of x is 1, so we have 1 dx. Derivative of tangent is secant squared. So we have that. So now all things x must turn into all things theta. So dx is secant squared of theta d theta. Denominator, 1 plus tangent squared of theta, quantity to the 3/2. So now we have done the trigonometric substitution part. Now it's all about simplification. 1 plus tan squared is secant squared. So we're going to have secant squared raised to the 3/2 d theta. And that step right there is the whole, this is why it works. We're taking these 2 terms, and the whole underlying concept is that those 2 terms smush into 1 term, and then that simplifies. We can do 3/2, we can take a 3/2 power of 1 term. You cannot take 3/2 power of 2 terms. You can't split this. Right? You can't distribute that 3/2 power. That's our problem. And so our strategy is, let's turn that into 1 term, and then we can simplify it. So does everybody see that this simplifies to secant cubed in the denominator? We multiply these exponents, so those 2's cancel. 3/2 times 2 is 3. So we're left with 1 over secant. And what is 1 over secant?
Cosine.
Cosine. An integral of cosine? Sine. Very good. Now we have to go back to x. This is where we draw that cool triangle. It's such a clever way to figure out what your how to go back. So tangent of theta is x. So right there, tangent of theta is x. So we draw the triangle, same triangle every single time. Draw it like it's in quadrant 1. Tangent is rise over run, is opposite over adjacent. That has to match. So we pick our angle theta down there. We look at the let statement. Tangent of theta is equal to x. There we go. That's it. Right? That is a picture of what that means up here. And now we do the hypotenuse. And that's going to be the square root of x squared plus 1. And that should match something up here. Yes, we see an x squared plus 1 there. Should line up pretty closely. If it doesn't, if it looks completely different, then there's a problem. And what is sine of theta? X over the root, right? So it's opposite over hypotenuse, so that's going to be x divided by the root plus constant. And now we've got back to the x's. All right, any questions there? So super important when you're doing your substitution step, that differential, make sure that that gets replaced. All right, you all start this one, get the trig substitution step all set up, and then go as far as you can. Go as far as you can. Let's give it a shot. Scream if you need help. Not too loudly, though. Took one of your pencils, Daniel.
Why would you do that?
I wouldn't. I'm doing
I'll have to count them.
What, you're 36? So the 36, when it comes out to the front, oh, you didn't factor that yet. So we know we're going to use tangent, but it's not just going to be x. So we don't So we have to make whatever this covariance constant is, we need to convert it to a 1 first. And that's what we are going to let be sine, secant, or tangent. Whatever's in there. So our first step is we have to get that 36 turned into a 1. So that means we have to factor that 36 out to the front. But whatever the power on that 36 is, that's going to come out on the right. So here, this 36 is in a root. So when it comes to the front, the square root comes along with it. So 36 to the 1/2 is 6. This 36, when it comes to the front, that power of 2 comes with it. So 36 squared. So whatever the power is, whether it's a half or Yep. Yes. Yes, so it's, yes, you do square it to take it out, so it's going to be, but it's in the denominator. Right? All right, let's go through that part. So the first step is we really want it to be a sum of squares with a 1. And so that 36 is going to get factored to the front. And a couple of things. Notice that that is in the denominator. So we want it to come out in the denominator. And notice that the power here has to come along with it. So if we pull something out, the power comes along with it, just like up here. Oh, not on this page. On this page. So here, we had a 4 in the denominator. The power on that 4 is a square root. It's a 1/2 power. So when it comes out to the front, it comes out with the power. And the square root of 4 is 2. Down here, where is the next one? Right here. This 36, it comes to the front, but it comes with the power. The power is a 1/2. So that has to come with it. So with this one, the power is 2. So this 2 is going to come with it. When we factor that 36 out, okay, the 36 is in the denominator, but that power right there has to come along with it. And you could square it out if you want and turn it into 1296 or whatever it is. I'm not going to do that yet because sometimes with trig sub you end up with cancellation later on. So let's see. So that came out, and let's focus on this denominator. So the 36 comes out of 36 and gives 1. There is no 36 here to pull out, so what it does, or what we can think about doing, is multiplying by 36 over 36. So the 36 right here, that and that are what come out to the front. So that 36 is coming to the front. We're left with z squared over 36. And then our goal is to write z squared over 36 as something squared. And what will that be? Z over 6 squared. So that will be how we use the algebra to get a sum of squares with a 1.
So when you pulled the 36 out and you took the square with it, the square went completely away from the denominator.
No, it should still be there.
Oh, okay.
Yeah, sorry. Thank you.
Okay.
Yeah, it should still be there. So it's this kind of thing. If we have something, let's do a different one that's a little less complicated. So if we have something like that, we want to pull that 4 out to the front. What we can let's do this in a couple of steps. So inside here, we can think of factoring the 4 out and just leaving it inside for a minute, like that. So if we factor that 4 out of 4 is 1, 4 out of x squared is x squared over 4. And then we're in a situation where we're squaring a product. So that square has to distribute, and it's going to go to the 4, making a 16. And it's going to stay on this as well. We'll make that x divided by 2, quantity squared. So the square has to go to each factor. All right. And now we're ready to do our trig sub. So z over 6, sine, secant, or tangent? Tangent because we've got the plus. We're going to differentiate both sides. The derivative of z over 6 is 1 over 6. And we have 1 over 6 dz. Derivative of tan is sec squared. We've got that. And now we're ready to turn everything we see in the inside of that integral over to thetas. Everything needs to become a theta. Before we do that, is there any question on the substitution or the factoring? So the z squared in the numerator. We look here, z is going to be 6 tan theta. So if we have z squared, that's going to be 36 tan squared. So that's going to be our numerator, 36 tan squared of theta. I notice one thing here that I want to change. Should these limits stay as whatever the original z limits were? No, those can't stay as z limits. You could leave them there if you wrote z equals, just to clarify that those are z limits. But usually I find it easier just to not put anything. We'll just go back in the end. Okay, so there's the numerator, z squared, rewritten as thetas. How do we rewrite the dz? Times 6. So we're going to go over there, solve for dz, isolate the dz, so we multiply both sides by 6. Now we go to the denominator. Tan is going to replace the z over 6. So we're going to have tan squared plus 1. So we're going to have tan squared theta plus 1, and all that is then squared. And tan squared plus 1, secant squared. And it looks like we have some simplification over here too. We are going to end up with out front, looks like 1 factor of 36 is going to go away here. And then we have a 6 over 36, so that'll reduce to 1 over 6. And we're going to have tan squared, secant squared, d theta, and down below we have secant squared squared, which is secant to the 4th. So let's simplify that. We'll get 1/6. And we get tan squared over secant squared. All right, so is everybody okay up to that moment? Any part of that substitution that you want to ask about?
Wait, why is it 1/6? Not
Uh-huh. What else? What do you think it could be?
I don't know what I did, but I got 1/3.
So we have a 36 here, a 6 here, and a 36 squared.
Right.
So the 36 takes away one of the 36s,
Right, but don't you have to?
and then we have 6 over 36.
Don't you have to pull out it like the 6 out of all of it?
This is all multiplication.
Oh, right.
So if it was addition, that would,
Then you-
yeah,
yeah, okay.
yeah, got it? Yeah, when it's multiplication, a little bit different. Any other algebra? Algebra snags. Linda?
36 tan squared. How did that?
So this is z to the 2.
Right.
So if we look over here, z is 6 times tangent theta. So if we isolate the z right here, we'll have z is equal to 6 tan theta. And then we're going to square both sides to get to z squared. You see it? And we're doing a similar thing down here with the dz. So if it helps you to isolate this before you start subbing it in, that's, totally fine.
Yeah, I didn't hear either. Square
This-
the z, and I was like, what is that?
So that, when we square that z, we have to remember to square both of those factors. Okay. We have powers of secant and tangent. We had a rule that said if the power of secant is even, that does not count as an even power of secant. It has to be up in the numerator for it to count as an even power of secant. So that is not an even power of secant. Or if we had an odd power of tangent. So this is neither. So it's that third case. If it's neither, we use the Pythagorean theorem to convert the tangents over to secants. So let's do that. And tan squared, again, we look at our triangle. Hopefully you have it ingrained in your brain by now. Tangent's right here, so the tangent squared will be secant squared minus 1. And strategy now. We will split the fraction. Split. So this will be the integral of secant squared goes into secant squared once. And what is 1 divided by secant squared? Cosine squared. So we'll end up with 1 minus cosine squared, which is sine squared. And how do we integrate sine squared? Power reduction.
Would it work if you did back up where you have tangent squared over secant squared? What I did is I converted that.
Sines and cosines?
Yeah.
Yeah, absolutely.
And then I got sines.
Yep, exactly. That will work perfectly well also. So right up here, if you wanted to convert, if you get to that case where tan's not to an odd power and secant's not to an even power, you could absolutely convert to sines and cosines. Yep. And you will end up with the same exact, yeah. And then I think somebody said it, to integrate sine squared, we power reduce. So we're going to factor out the 1/2, and it's going to be 1 minus cosine of 2 theta instead of 1 plus cosine of 2 theta. So the power reduction has a 2 in the denominator, so that 2 in the denominator is combining with the 6 in the denominator to make the 12. And now we integrate. The integral of 1 is theta. The integral of cosine is sine. Angle is linear, so we do reverse chain rule. Does that integration work for everybody? So integral of 1 is theta, because the derivative of theta is 1. Integral of cosine is sine. Cameron? So the identity that we're using has a 1/2 in it. So we have that sine squared is 1 minus cosine of 2x over 2. So that division by 2 comes out and combines with the 6 to make the 12. Good to go? So once again, we see that we're going to use the double angle for sine. We're going to have theta minus 2 sine theta cosine theta divided by 2, star to double star. 2's cancel. Now we're ready for the triangle. Our portal that takes us back and forth between x's and, or whatever the original letter was, maybe it was a z. I hate z's. All right, so z over 6 is tangent theta. So we'll come over to the side. Z over 6 is tangent theta. So there is our triangle, quadrant 1, theta in the corner. And the triangle needs to satisfy this equation right here. Tangent is rise over run. Then we just have to figure out the hypotenuse. And the hypotenuse is, move that over a smidge. So the hypotenuse is the square root of 36 plus z squared. And that should match something up in here, z squared plus 36, whatever order you write it in, obviously doesn't matter with addition. So we have 1/12. When we look here, theta is going to be equal to inverse tangent of the other side, so inverse tangent of z over 6. So that's what goes right here, inverse tangent z over 6. Back to z. All right. Distribute that 1/12 all the way across. So we're going to have minus 1/12 sine of theta. What's sine of theta? So we're going to do the opposite over hypotenuse. So we're going to do z over the root. So z divided by the square root of 36 plus z squared. Cosine of theta. So we're going to do 6 over the root. Plus the constant of integration.
Wait, isn't it like from?
Oh, are we doing a definite integral? Thank you. We are doing a definite integral. So it's from, it was so long ago, 6 and 6 root 3. Okay. Let me just draw a circle up here because we're going to have to do some inversing. Some inversing. All right. So we know on the 12-sector circle, the slope at pi over 3 is root 3, and the slope at pi over 6 is root 3 over 3. If you take your coordinates, root 3 over 2 and 1/2, and you divide them appropriately, that's what you get for the slope. That's what tangent is. Tangent and slope are the same thing when you're looking at the terminal ray of an angle. So let's see. This first thing says 1/12 inverse tangent of root 3. Let's just write it out first. So inverse tangent of root 3 says the angle on the right with a tangent value of root 3. What is the angle value on the right that has a tangent value of root 3? Pi over 3. So this is going to be pi divided by 36 minus. All right, so here we're plugging in 6 root 3 for the z. So in this numerator here, we have 6 root 3 times 6. 6 root 3 times 6 is 36 root 3. And in the denominator, the two square roots multiply and the square root goes away, so we just have whatever's inside. So we have 36 plus z squared. And that squared is 36 times 3. That's a time symbol. Everyone follow that? If we square that, we square the 6 and get 36. We square the root 3 and get 3. Any issues there? 1/12. Z is 6 root 3, so that's 36 root 3. Square root times square root, the square root goes away. We have just what's inside. And 6 root 3 squared is 36 times 3. We can cancel a 36 here. 36 goes into 36 once, goes into 36 once, goes into 36 once. So because that denominator has a sum, we've got to cancel it across both of those terms. So we have pi over 36. What are we left with over here? It looks like a root 3 in the numerator. And in the denominator down here, this is 1 plus 3. 1 plus 3 is 4 times 12 is 48. And that's about it.
What about the
Oh gosh, we're not done yet? I want this problem to be done. This problem's taking forever. Okay. Right. The lower limit of integration does not give us 0. So we have to plug that thing in. All right, so we're going to subtract off 1/12. Arctangent of 1. And what's arctan of 1. What's arctan of 1?
Oh,
Pi over 4. Arctan of 1 is pi over 4. Plus. So subtracting a negative gives us a plus here. So we're going to have plus a 12th. When we plug in the 6 here, 6 times 6 is 36. And then how about that denominator? What is that? That denominator becomes, so plugging in a 6, 36 plus 36. 36 plus 36 is 7, this is like 6 root 2? No. Wait, you guys disagree?
yes.
Shouldn't it
Darn.
be 72?
So let's see. So
No, there's no root.
Yeah, why did we have a
Yeah.
there's no root anymore.
Roots cancel.
Because the root times the root cancels, right? If we have root times root, we get that. I guess if I let what's inside be a blank, then that's what we get. So if we're doing the inside, we have 36 plus 36. So that, oh, did I leave the root in?
Yeah.
Oh, I am the bad one here. So what should that be? 72, thank you. 72. I agree with you. Okay. And you already told me that this is pi over 4, so that's minus pi divided by 48. And then this would be plus, the 36 goes into here once, it goes into there twice. So that's 1/24. We agree with that one?
I think so.
Me too. I think so too. So we could get some common denominators and do some things, but we're not going to do that today. If you were in my math lab and you, well, even my math lab's doesn't force you to simplify actually. Usually. All right, we're sick of this problem. Any questions on it before we Leave it behind.
So it's okay that that's a negative number?
So, let's see, let's go back to the original. So this function here, everything in here is, if we were to graph this function, if we were to graph it, that's definitely a positive valued function, right? If you were to graph x squared over x squared plus 36 squared, that's all positive stuff. And that interval is over in the x direction. That should be a positive number. So, did you type all that in and you got a negative?
I didn't type it in anywhere, I just did it on my own and I got a negative.
Huh.
I got pi plus 24 minus 48 root 3 all over 144.
So here's what I see. So this denominator is smaller than this denominator. So this fraction is bigger than that fraction. So that pi fractions are definitely positive.
Yeah, pi is positive.
So this denominator, if you make that a 48, you're going to have a 2 up there. And 2 minus root 3 is positive.
Okay, so.
Because root 3 is like 1.8 or something.
Alright.
Yeah, so it is positive.
Yeah.
But that's a great question. What's that, Daniel?
It shouldn't be minus 124.
Say that once again.
The last one we just repeated. Oh,
Yeah, it's minus.
Oh, that sign right there?
yeah.
Yeah, so that's because we subtract off the lower
Oh.
limit, so minus becomes, you see it?
Yeah.
Yeah. Let's see if we can somehow do one more of these without going insane. Okay, trig sub. Now here they give us this thing that says x is greater than a half. That's just so that this square root is not a square root of a negative. All right, if we plug in a number that's less than 1/2, this square root would be negative. Obviously, that's undefined. But our focus is in here, and we have a difference of squares. It already has a 1, so that's good. But it's not quite written as a difference of squares yet. There's one modification to make this a difference of squares. We want to write this as 2x quantity squared minus 1. So now it's written as a difference of squares. 2x squared minus 1 squared. So that is a difference of squares. Sine, secant, or tangent? Secant. Secant, because secant squared minus 1, right there, secant squared minus 1 is tangent squared. So we are going to choose secant. We are going to let 2x equal secant of theta. Take the derivative of both sides. So we'll have 2 dx is equal to secant theta tangent theta d theta. And now we're just going to plug all those thetas in. All things x become all things theta. So inside this square root in the numerator, the 2x becomes secant, so that's secant squared minus 1. The dx becomes 1/2 secant theta tangent theta. So we're replacing this dx right here. That's going to be 1/2. So I'm going to pull the 1/2 out to the front. So let's put a 1/2 right there. And that, oops, sorry, got that. So this is going to be times secant theta tangent theta. D theta. Denominator is x squared. So we have to look at the original substitution, isolate x. So if you have to write it out, write it out. If it doesn't, if it's not going to be super easy to do it in your head, then just write it out. So x squared is going to be 1/4 secant squared, or secant squared over 4, however you want to write it. Secant squared theta over 4. Daniel?
Don't
Don't we have to divide by 2, like dx divided by 2?
And that's what this is.
Oh, I see.
You see it? So, yeah. So the dx right here is secant tangent divided by, so I just moved it out to the front right away.
Oh.
Yeah. Trying to psych you out. Just because it's fun. All right, any questions on the substitution thus far? All right. When we flip this fraction, the 4 jumps to the numerator, comes out to the front, and makes the leading coefficient a 2. So that takes care of the constants. Secant squared in the denominator, secant in the numerator, that leaves us with 1 secant in the denominator. Secant squared minus 1 is tangent squared. Square root of tangent squared, tangent. Tangent times tangent is tangent squared. I feel like we actually just had this one a moment ago. Is this identical to the prior problem, the end of it? Where we ended up with...
No, we had tan squared over
Oh, tan squared over secant squared. It just looks so familiar. Okay. But it's a similar thing where we don't have secant to an even, we don't have tangent to an odd. So the 2 strategies are convert the tangents with Pythagorean or change the sines and cosines. Either one of those strategies will work. So I'll convert these tangents to secant squared minus 1 because it's so helpful to get really comfortable with that identity. You could change the sines and cosines for sure. And then we're going to split the fraction. And we should have that. So secant squared over secant is secant. 1 over secant is cosine. Integral of secant. Natural log absolute secant plus tangent. Integral of cosine. Sine. Bless you. All right, so that's what we end up with. And now we just need a portal to get back to the original variable. Original variable is x. There's our substitution. Secant of theta is 2x. So let's come over here. Secant of theta is 2x. Same triangle every time. Put a theta right there like it's in quadrant 1. Secant is hypotenuse over adjacent. So hypotenuse over adjacent needs to be 2x. So hypotenuse over adjacent needs to be 2x. Then we find the missing side. So hypotenuse squared minus leg squared. And if we go back to the original, it should look similar to something up in the original, and it does. So we will have 2 natural log absolute value. Secant of theta is 2x. Tangent of theta, opposite over adjacent. So that's nothing more than the square root of 4x squared minus 1. And I'm distributing this 2, so we'll have minus 2 times sine of theta, opposite over hypotenuse. So we're going to have square root 4x squared minus 1 divided by 2x plus c, and we'll have a 2 that cancels right there. And that's as far as we can go. Wowza! Trig sub. Trig sub is one of these super, like as you do it and you start getting some right answers with trig sub, you get this warm, fuzzy feeling inside. It's like when you do a trig sub problem all the way through and you get it right, it's like it's one of those things. You're going to experience it like before Thursday, I hope. I hope. On the snow day tomorrow, look for that fuzzy trig sub feeling while you're trapped in your house.